Okay, so today we're going to aim to do important questions. I'm never going to count how many questions there are. Okay, but generally the tutorial is quite important. Okay, so we have to focus on this. Yeah, I don't actually remember if we've done question 4. So perhaps I need you guys to turn over to question 4 first. Okay, let's try and see whether we've done a bit, right? Okay, we have done a bit. Okay, then I guess we do one more part, right, before we move on. Okay, so let's start with question 4. Okay, we have done part A and part C in the previous lesson. Okay, today let's try part E. E is a little bit more challenging than the previous two because there are a little bit more steps compared to the previous two examples. Yeah. Okay, let's do a quick recap. When we do reaction synthesis, right, I need you all to remember a few things. Okay, this question type is called reaction and synthesis. Okay, as we know, right, the direction of each one of them is different. Well, let's just say a reaction of halogen alkanes. Are you going forward or coming from behind? No, reaction. Let's say reaction of Rx. Yes, there is Rx reacts to form other stuff. But guys, what does synthesis mean? The synthesis of Rx. Yes, you're trying to make Rx, right? So whatever turns into Rx, that is synthesis. So remember, that's what we're going to do for this question. Okay, perhaps I need you all what to start with, right, is to look at part B, and I need you all to draw the skeletal formulas for both the starting and the ending product. Okay, but again, before that, right, okay, there's one more thing that I always tell you guys to do for this kind of question. Always count the number of carbon atoms in the starting and ending product, because sometimes the number of carbons can give you a lot of information and it can simplify your question by a lot. So perhaps take a look at bromine and 2-methyl propanoic acid. Okay, look at these two structures first. Go and draw them out, okay, to half the thing. Okay, then afterwards, okay, we can slowly check what to build in. Okay, bromine is 3, butene is 4. Okay, please remember that, right? Okay, 2-methyl propanoic acid. Go and draw propanoic acid first, then fit your methyl group on the correct position. No, finish it. Yesterday I checked left 1, then I finished it. Yeah, that shit is good, right? Yeah, I more.
So you like every year come over Korea?
No, not Korea, fuck Korea. I'm not going there again.
Why?
The people suck. The people there suck.
Actually,
the people there are just foreign.
like
what the food? The food is like only like I wouldn't go back there again. They are not nice at all. Like in general, the dinner just sucks. Yeah.
And you like
Yeah, that's why I'm not fuck area. But Japan, people there are actually nice.
But Japan,
the food are nice. The food is nice. So nothing very good. Draw the blue factors. Oic acid, oic acid. Remember, oic acid is your CO2H. Okay, carboxylic acid, CO2H. We have already learned that functional group in this chapter. Okay, so I've seen you guys have gotten protein. Okay, so that's the first stage. Then afterwards, right, okay, we will end up with 2-methyl propanoic acid. Okay, go and draw that first. I think some of you haven't drawn that. Okay, I've seen a few already. Okay, very good. Okay, so we have to draw propanoic acid first. Okay, which looks something like this. Okay, you all can write CO2H, but I think I'll prefer to draw up the whole thing. Okay, but of course, it's on the second carbon, 1, 2, so over here. Now, of course, I told you guys to count the number of carbon atoms. CO2H can also. Okay, but I prefer this sometimes. Okay, so I ask you guys to count the number of carbon atoms. So what should we do here? What do you notice? Is there anything special over here? 5 carbons away. Okay, this one started off with 3 carbons, right? And then this is 4 carbons. Guys, do you remember what does this mean? If there's an increase in number of carbon atoms, it's also informally known as the what kind of reaction? Okay, it uses a CN, okay, good. Okay, but in other words, right, in general, this is called a step-up reaction. And in your syllabus, right, you're only going to learn 2 step-up reactions in total. Right now, we have only learned 1. Can you remember what that reaction is called? Okay, the one you say is Cn minus, okay, good. What is Cn minus doing? It's replacing something. Okay, what's this topic all about? Okay, this whole topic is about replacing halogenal alkanes, right? Okay, if you have a halogenal alkane here, you want to turn it into a CN, a nitrile. In other words, this is your nucleophilic sub. In fact, that's the only reaction that's happening in this topic. That's like the main reaction, I wouldn't say it's the only reaction. Okay, what I'm trying to say is this, okay, you have a substitution of the halogen here, which means to say, guys, if this is the only way you can increase the number of carbon atoms, that means this reaction is guaranteed to happen somewhere in this process. Does that make sense? Your job is to just fit that reaction in, but you do not know where the reaction is now. Okay, you need to find a halogenal alkane first, and then you can proceed to a nitrile. So you have pretty much shortened the pathway up. Instead of getting from this to the end, now your goal is much easier. Get from this to this first, and then later we can proceed over to this. So our job right now, how do we turn an alkene into a halogenal alkane? Electrophilic addition, okay, good. Okay, so what do we add over here? What's the reagent we add exactly? Okay, what do you want? You want to use bromine, chlorine, or you want to use? Okay, if you use chlorine, guys, okay, you put Cl2 over here, I will end up having 2 Cl atoms there. Is that possible? Do I want 2 Cl atoms? Not really, right? Okay, I only want 1. Hello? Okay, I only want 1 Cl atom, right? Okay, so what can I be adding? Instead of adding 2 Cl atoms, how many Cl atoms do I add? Half. No, that it doesn't work like that. Okay, it's not about mole ratio here. Okay, some no mole ratio. Yeah, okay, no, not Cl minus. Guys, you all have to remember your electrophilic addition is Cl. You need to go back and look at your alkenes. If not, all these things I cannot help you also. Okay, this one I think Cl gas, we can at room temperature. Okay, from there, right? Okay, I want you guys to try the other product. Okay, go and try to synthesize this pathway. I've told you guys enough about the procedure already. Okay, step-up reaction is already such a huge clue. So you guys, I've already shortened the pathway, right? Try to get a halogenal alkane. Okay, the rest go and try yourself. Okay, I'll give you guys a few minutes. Okay, your notes are already at your disposal. Okay, just use it. Okay, eventually you still need to memorize all these reactions. Okay, but for now, I'm just going to. Sorry? Okay. Wow, I will go for it.
How much battery?
Okay, try this question first. We are trying to synthesize this. Okay. What happened over here? In readers and conditions, okay, unfortunately, you might need to refer to the notes, okay, because you guys haven't memorized it yet. Not to worry, okay, because we already only saw this for like once. Okay, I just minimally want to see the structures first. You want to discuss whatever again, you can just go ahead. Okay, I just want to make sure you all know how to get it. Yeah, so you want to do things really. Okay, guys, I just want to mention some stuff for reaction synthesis. Okay, as you can see, right, okay, you are learning new reactions. There are a lot of reagents and constants. Right now, halogen derivatives is the midway of organic chemistry already. And if there are this many reactions, right, you can already imagine there's going to be even more reactions because we are only in the midway point. So I suggest you guys from now let's start this. Okay, we need to memorize reactions starting from now. If you wait until the exam, I'm sorry to say, but you are going to struggle a lot with trying to memorize the reactions. Okay, it's an ongoing process. Okay, so that's why we have to start this now. In order not to suffer for this kind of small little reagents and conditions thing, I really need you guys to go and write down all the reactions, right? Okay, from every topic. So it's a very topical thing. You can even make like some sort of flow chart, mind map, whatever. I don't care what format, right? But all I need you guys to do is to go and write down all these reactions on a separate piece of paper. You go and consolidate all these reactions. Okay, I can teach you guys how to do it more effectively. Okay, number one is to split it according to topic, obviously. Okay, but afterwards, right, you all need to go and split it based on the functional groups and the different reactions. Okay, and I already mentioned, right, okay, you can split it based on reaction and synthesis already because that's really how my books are split up for these two portions. Okay, every functional group has a reaction for it and how to synthesize it. So if you split it according to this format for alkanes, arenes, and halogen derivatives, we've learned 4. So far now it's not that bad. If you start the work now, right, then you can consolidate, you can compile and go on top of it every single time, every single topic that you've learned. The next topic is alcohols and phenols. That topic doesn't have any mechanism for it, but that topic has a shitload of reactions. I can tell you all first. Okay, so if you start the next topic onwards, I can tell you it's going to be quite bad. So I'm going to tell you all this now. Okay, every reaction, every synthesis must be there, and you must focus things in your basically in your revision. The first one is you need to know what type of reaction it is. I don't care whether it's electrophilic addition, electrophilic sub, nucleophilic sub. We've only learned 3 so far. The later you start, there's going to be 4. Okay, the second thing we need to know, right, is kind of like, of course, the reagents importance. But more importantly, right, I want to see the equation. The equation doesn't need to be balanced. The equation can probably look something like this. Yeah, okay, it's clearly not balanced. You want to balance it out. Okay, but all I'm trying to say is that at least you write out something so you know exactly what's happening. So for example, we know that nitriles can undergo different reactions, right? Like one of it is reduction. You want to do something like that also can. It's quite rare for the exam to ask you to write balanced equation. That's why I say it doesn't really matter all that much if it's balanced. Of course, it does come out. Okay, so it's really up to you. But more importantly, I just want you guys to know exactly what it turns into. By writing all this, right, and by writing it for all the reactions, I can tell you that it does help. It does help you memorizing all the reagents and conditions. Eventually, right, you just associate, oh, HCl gas is what I'll okay, eventually it will happen. But how does that happen? You need to know. Okay, just spam all this right onto a notepad or something, right? And then eventually this one will all come naturally, and then you won't have to keep referring. Okay, start now. Okay, that's my advice. Okay, depending on whether you all actually start or not, right? I'm not gonna enforce because I'm sure you're J2 now. Okay, I don't need to actually enforce that. Okay, but basically, if you start things off here, that was the first reaction. How do we know the first reaction has to be HCl? Let me just repeat this one more time for the sake of this continuity. Okay, we have that reaction that is definitely guaranteed in this pathway. Since this reaction is bound to happen, we must get this thing first. So instead of thinking from start to end, we think from start to halogenal alkane. That's what we have gotten so far. Can you see that? Okay, now The Cl must be on the second carbon. It cannot be on the first carbon. Any idea why? This is your alkenes ready. The Cl must be here because this right here is your major product. Can't remember why is the major product. Okay, must go and revise the alkenes ready. Okay, no choice. In reaction synthesis pathway, you must give me your major product. Okay, that it must be major. Okay, so whether it's major or minor, right? Eventually you get the final product. Okay, what do you think is the next step, guys? What's the next course of action? What do we do? This thing that has to happen already. Okay, that's why I say step up reactions, you must count carbons first. If you all count carbons, you all know this will happen. And when this happens, your answer is all there. It's all laid out for you guys. So I'm going to substitute the halogen with the nitrile over there. As for reagents and conditions, eventually you guys will remember one. Okay, ethanolate, NaCN, and heat. Something similar to this. Again, I don't think reagents and conditions are very difficult to memorize in the first place. Okay, because they do make sense in the context of what you do. Okay, but now your final step is there a way, right? We can go from nitrile all the way to a carboxylic acid. That possible? Okay, again, look at this thing over here. Either reaction or synthesis, right? Okay, guys, this is reaction or synthesis of nitrile. If from there you're going forward, right? So it's what? Okay, reaction. Good. Okay, how about this? This is the synthesis of a carboxylic acid. Have we learned the synthesis of a carboxylic acid yet? We haven't touched on that topic yet, right? Okay, so the only choice that you guys have is the reaction of the nitrile. Have we learned any reactions of nitriles? Answer is yes. What reaction is this? Okay, we can turn this guy straight into a carboxylic acid. Or what is this called? Okay, good. Acetic hydrolysis. Okay, so remember the name of the reactions, guys. So when you do a revision that time, this is what you need to do. Let me give you guys an example here. Okay, under reaction of nitrile, the type of reaction here is acidic hydrolysis. The reagents and conditions here is acid, obviously, H2SO4. Okay, must be equal state because there's hydrolysis. And I need to heat also. Okay, and finally, an equation will look probably something like this. Okay, from CN to CO2H, we just need to tell me H2SO4 equals. And guys, when you're doing this procedure, this 1, 2, 3 step procedure, you cannot just copy straight from the notes. I'm sure you all know that. I just want to make sure you all don't just copy straight. You need to at least browse through the notes once first. And then let's say, okay, Hashish's notes here got the nitrile. Okay, you see through it once first. Okay, and then you cover it, right? And then you try to write all this for all 3 reactions. That's the only way it can go into your head. Okay, in class, I already told you the reactions. You guys can confirm understand. But it's the next step, which is so that are you able to replicate that? Are you able to produce that information onto a piece of paper? That is the second step, really. Okay, so I'm teaching you guys how to study. Okay, to study organic chem, right, you might need to adopt this slightly different approach. Browse through it and try to write the same thing down. Okay, that's input and output. Okay, that's the most important manner. Okay, can so far? Oh, good. Okay, I want you guys to try another part. Okay, very quickly. Okay, we don't have much time to just dwell on this question. Yes. Okay, how do you get a methyl group? Okay, if you look at the arrangement of this particle, right? When I add H2SO4 and heat, do you agree that CN becomes CO2H? Okay, but do you notice that this is the exact same structure as this? It's just rotated. Okay, you can see. Okay, CO2H is here, but then you can number the carbons. If let's say this is carbon number 1, this is carbon 2. Carbon 2 is ordered to 3 and 4. It's branched to 3 and 4. This is carbon 1. This is carbon 2. Carbon 2 is branched to 3 and 4. It's the exact same thing. Sometimes if you have troubles seeing it, right? I suggest you use numbers. Number the most notable thing, which is in this case CO2H. Okay, you rotate this thing, you get that already. Okay, okay. Okay, so that's the rough idea of this reaction. Good so far. Okay, now that this is done, we're going to proceed to another part. Okay, this is only part B. So I want you guys to try part F as well. Okay, apply whatever I just told you guys. Okay, there's the reaction of 1, synthesis of 1. So on, so forth. Sorry? Okay, build is 4. Okay, good. You'll just need to remember the first 4 rules. Okay, you all just need to remember the first 4. Okay, because everything after 4, right, you all just need to know the shape. Like, guys, what's the 5-sided shape? Pentagon, so pentene, right? Okay, then a 6-sided shape is hexagon, so hexene. Okay, so everything from 1 to 4 is all you need to remember. Can you see that? Yeah, okay, it's very easy. Okay, go draw the compounds first from start to end, right? Okay, I'll give you guys like about 3 minutes. I'll try to figure this out. Okay, let's not take longer than 3 minutes. Count carbons up, count carbons. HF, how many carbons? Two. Two, 3 is prop. 2 is ETH. Okay, and then CO2H. Yeah, try. Yeah, I know sometimes it looks a little bit weird from the perspective, but it's actually not like that. Yeah, suggest the CO2H, you draw the bonds out, then it does look a bit more legit. Like draw the CO2H bonds out, then it looks better. Okay, so for butyl-1-ene, butyl-1-ene, I'm sure you all can draw this. Okay, but ethanoic acid has 2 carbons, right? So 2 carbons just looks like this. And then on one of the carbons, you just put your CO2H. Like this. Yeah, okay, so that right there is ethanoic acid. Okay, this looks more legit, right? Okay, you put CO2H there, looks a bit odd. Okay, so that's why I recommend you guys draw the bonds. Try not to write CO2H if possible.
That number can be on the one.
Okay, can also. Okay, I'm gonna guide you guys through a little bit, then the rest I need you all to do yourself. Okay, I saw you drew 3 arrows. How do you know there are 3 steps? That's the thing. Or the question is so, or did it?
Yeah.
Oh, okay, fair enough. Okay, they give you a hint. But in the exam, no hint. Okay, so let's not be too reliant on that. Okay, let's say we do not know how many steps there are, which is more realistic. Guys, how many carbons are there? What happened to the number of carbons? Okay, it actually decreases now. Okay, in this topic, right, I have not talked about what do you call this? Step down reaction. Okay, I have not talked about step down reaction in this chapter at all. This one is a slightly challenging question. Okay, but let's think about it. Okay, we don't have step down reactions, but we actually have learned it before, right? In one of the 4 topics. Alkanes, alkenes, halogens, and arenes are one of these reactions we got learn step down. There is one way to cut a compound. Can you all remember that reaction? Where you can cut the compound into smaller fragments. Not elimination. Elimination, you're removing HX. HX doesn't cut the number of carbon atoms. It's in alkenes, that's the clue. Alkenes can undergo this reaction where you can cut the number of carbon atoms. Okay, that's the only one we have learned so far. It's something to do with books. Yes, I see. I said books, then you think of this. God damn it. Yeah, okay, someone else think of one. Yeah, sure. Yes. Okay, what's the full name? What's the full name? Something cleavage. Wow, no lah. Oxidative cleavage. Okay, it's oxidation reaction. Your school might teach you guys strong oxidation, but no one remembers that shit. See, you will immediately remembers it the moment I say books. Okay, so oxidative cleavage. Okay, you are cutting bonds up. So because you are cutting bonds, right, you are actually cutting the number of carbon atoms also. Now in this case, it's quite obvious that I have to somehow cut the number of carbon atoms, and this applies to alkenes. So guys, can you look at your what's this? Your flow chart right now? Do you have an alkene at the moment? Yes, it's at the start. Okay, guys, perhaps let's just perform debate here. Okay, so why not we cut the double bond? Okay, guys, how do we cut this double bond here? Okay, we cut like that, right? Okay, then what next? Okay, guys, let's come out with the 2 products first. The carbon at the far end, what does it become? Good. Okay, carbon dioxide. Because guys, an alkene that is at the end, right, is called what alkene? Start with T. Yeah. No, not tertiary. Tertiary means the terminal alkene. Okay, guys, please take note. It's called a terminal alkene. Terminal means at the end. So at the end of a carbon chain, okay, there's a terminal alkene, and terminal alkenes always form carbon dioxide. Please recap this. I'm going to tell you this cheat code right now. Okay, don't forget. Okay, so if one of them becomes carbon dioxide, then how about the other 3? What happens to this carbon then? The double bond becomes double bond O, and then the H becomes OH. Okay, that's how oxidative cleavage works. You add an O to the double bond, and if there's any H attached to it, you must add an O to it as well. Okay, guys, is this the product that you want? Is this the carboxylic acid that you want over there?
No.
The carboxylic acid has 2 carbons. This one. So clearly that's not the answer now. Okay, it's not a one-step procedure. Okay, somehow, right, there's something we need to do to it first before we can perform oxidative cleavage. We know this will happen. Okay, but clearly this is not it yet. So guys, how? Then another option over here. I want you all to think about it. If I cut the double bond over here, I get a fragment that's 3 carbons and a fragment that's 1 carbon. How big is that fragment over there? Okay, so I want you all to exercise your creativity here. How are you going to cut a double bond such that I get a fragment that's 2 and 2? Good, the double bond must be in the middle. So now I have shortened my pathway to, instead of coming from here, I come to here. Can you see that's my immediate most, like the most recent path, my most recent compound? Because the moment I cut this in the middle, I have 2, and each one of them is the exact same product, this carboxylic acid. Now my pathway has been shortened up. Instead of coming from here to the end, it's only until here. How do I change the position of the double bond? That's the question now. How do I change the position of the double bond? Okay, have we learned a direct reaction that can change the position? No, no such thing. It's not magic. What should we do first? What could we do first? If the double bond at the start is not there at the end, that means what can we do to this double bond first? Okay, we could break the double bond by doing what? Let's not cleave it up, okay, because it still has 4 carbons. What should we do? What else could an alkene undergo? Okay, you can just undergo addition, right? Okay, why not let's add something. Okay, what do you want to add? Let's just do the same thing as just now. Okay, if you add HCl, where do the Cl atom go? Which carbon? There's this carbon or this carbon?
The one.
Okay, the one, this one, correct. Okay, this is the more stable carbon-cation ion, that's the major product also. So I have now successfully gotten rid of the double bond from the initial position, but now somehow I need to produce that exact same double bond in another position. What should we do now? I've undergone addition over here. What should I do next? Why not I get rid of it again? Can you see that? If I get rid of the same HCl and via elimination, I can get that double bond on a different position. Does that make sense? So by adding it, by eliminating it, I can get that. But then some of you may be asking me this. You eliminate this Cl, where do you eliminate the H to get that double bond? Yes. Okay, you must remove the H from here such that the double bond can be formed between these 2 carbons. But is it possible for you to remove a H from here also? So it's also possible for you to get this product over here, right? You can get the initial product again. It's entirely possible in real life. But now, right, let's not consider that possibility because we want to get this one. So we just assume we can get this. As long as there's a way to get this compound, let's just do it. We don't ignore, we ignore every other product. It's possible. So that's the answer to this question. Okay, so I want to take note. Why I go through this question with you guys is because whenever you want to change the position of a double bond, you just need to edit, undergo addition, then elimination. Okay, can? Okay, so I want you guys to fill in the other reagents and conditions, and then we can move on to other question types already. Okay, can? Right, what's the reagent and conditions? Okay, some of it is in other topics, so you can't find from the notes over here. Okay, can you remember the condition for elimination? Okay, but there's other stuff you need to do also. Yes. Okay, from now on, okay, go and remember that your elimination is ethanolic NaOH. Do not write the aqueous there because it's a different medium and heat. So when you do your revision that time, the 3 steps, you tell me type of reaction, elimination, reagent and conditions, you write both that down. Equation, then you can do something similar to this. As long as you fulfill these 3 things, that means you have that reaction package already. It's settled. Okay, now next one over here. Oxidative cleavage. Can you remember what you need? Oxidation in general, you need to add a what? Oh, no, not oxygen. A what? It's 2 words. To oxidize something, you need to add what? oxidizing agent. So what's the most powerful oxidizing agent that you guys know? Okay, KMnO4. Okay, guys, other than KMnO4, what do you need to add up? Okay, heat, of course, but there's one more thing. Okay, you need to heat because you need to break the whole double bond, and that's not very easy. But at the same time, you guys must add, yes, good, H2SO4. Please take note, H2SO4, KMnO4, and heat is a package, very, very common package. Why you need H2SO4 is because KMnO4 by itself won't work. It needs acid, then it can work. Okay, that's just how it works. Okay. Now, reaction synthesis done. Again, I say this kind of questions can do one get as long as you study. Okay, can you all turn over to page 5? Sorry, question 5. Question 5 is something we've already touched on in this chapter. Okay, look through it first. Okay, think about the answer. 2 minutes. Okay. Now you feel like you have probably seen this happen somewhere in this topic. Okay, so go and find. Okay, perhaps I suggest I'm going to draw the 2 skeletal formulas. Okay, I see some of you are trying to draw structure. It's taking very long. In exam, we don't have that time. Okay, so I want you guys to practice skeletal from now on. Okay, you're going to count how many carbons, then just draw that carbon skeleton first.
Is it the FN or
Sorry?
what is that?
No. But I mean, nothing to do with that. SN1, SN2 both can react. Okay, in this case, one can react, one can't react. Okay, draw the structure first. You might see something. Okay, so some of you are drawing low. I guide you guys through. I don't want to throw the answer at you guys first. Now, they say this structure over here can react. This structure here can't react. I need you guys to just tell me what exactly is the difference between these 2 structures. Is this a halogen alkane, the one that can react? It is, right? Okay, this is just a CDR bond, it's a halogen alkane, right? But isn't that a halogen alkane on the right also? But why is it that this guy can't react? Again, guys, halogen alkanes can react. They just use the word reactive. What is the reaction that they are undergoing anyway? What reaction? What's the main reaction we learn in this topic? Okay, nucleophilic substitution. Okay, the question is saying this guy can undergo nucleosub, but this guy cannot undergo nucleosub. Why? Look at the guy that can't undergo nucleosub. If you cannot substitute this bromine away, it implies what? Yeah, that's the answer. Okay, but there's a bit of steps that we have skipped there. Okay, so remember what we went through before I talked about partial double bond, correct? In order to substitute this guy, what must happen to this bond here? What must happen to this bond in order to substitute? Wait, you need to break the bond. If you cannot substitute, means the bond cannot break. And why does the bond not able to break? Exactly. Somehow, this bond is way stronger than this exact same bond. Can you see both of them are CR bonds? But yet, this guy somehow has to be way stronger to the point where it just can't break. What gives this guy, even though they look exact this, the extra strength? What give it the extra strength? It's what you just mentioned, partial double bond character. This guy has some characteristics of a double bond. Remember the analogy I used? Imagine your parents, right? Okay, they are African American. You're clearly gonna share some genes for them. You're gonna be taller, bigger, stronger, right? They're physically stronger. Okay, compared to let's say I Chinese genes, cannot do shit, okay, then weak. Okay, but you take a look at this right here. Okay, this guy is a normal single bond, but right, he's very weak. But why is he much stronger? Because he has some genetics, right, of the double bond. Okay, and how does this appear? How does partial double bond come about? I've already done the explanation with you guys in the notes. Okay, so we're gonna recall that. Okay, or perhaps let's just draw the diagram now. Okay, come to this diagram here. What happens? Okay, so guys, in our notes, what did we learn? We learned that partial double bond character arises from when a halogen is attached to a benzene, right? But how does that actually happen? It's not the fact that it's just that. What actually happened? You bring me through the process. Okay, but before delocalization can happen, what must happen first? Okay, good. This carbon has a p orbital, just like the other carbon atoms inside it. This guy also has a p orbital, and this p orbital inside has a loop back. Okay? What can they do first? Okay, they are side by side, they can overlap, right? And once they overlap, then what happens to the loop back? Then the loop back can delocalize into benzene. The act of doing this, right, will result in partial double bond, right? You can see that. So it's now strengthened. But now you have to realize, right? In this case, do we have the exact same scenario? So it's not about benzene, it's about the fact that it's overlapping p orbitals and delocalization. Okay, so let me just come up with a simple idea. P orbital overlap plus the fact that there's delocalization of electrons equals to partial double bond character. So don't just look at it in terms of, oh, isn't it just for benzene? No, okay, let's just try to apply this onto somewhere else. That's what exam questions will do. Okay, they'll give you an unknown idea, but we have to learn the hidden concept before. The underlying concept is the same. Guys, take a look at this structure there. Okay, perhaps you want to draw the exact same diagram. Draw a little bit bigger. Okay, what do you notice over here? This carbon and this carbon, what hybridization are they? The one in the double bond. Just like in the benzene, same one. What's the hybridization of the carbons? Okay, sp2, sp2. If they are both sp2 hybridized, that means they have a p orbital. Yes. Okay, both of them have a p orbital each. And guys, that's the initial reason why there's a pi bond, right? That's how the pi bond came about. But at the same time, because this bromine is directly attached to a double bond, what will happen? This bromine directly attached. He also has the p orbital. What happens to this p orbital? Can he overlap? They can overlap, they're literally side by side. So what's happening here is the low pair of bromine will delocalize into this high electron cloud. It's the exact same scenario as this. Exact same. So let's explain this. Okay, your job over here is to first tell me the p orbital of bromine does what? Come, write down the answer with me. The p orbital of bromine overlaps with what? Overlaps with the, okay, you can call this the pi electron cloud of the double bond. It's just like you tell me pi electron cloud of benzene. So remember this concept. Okay, it's not a hard concept once you all understand this. And you all just need to remember the keywords, right? And then answer always correct. Okay, but once this happens, the next stage, you must tell me delocalization of the electrons. Lone pair of electrons on bromine delocalizes into the double bond. And this results in what? Okay, this causes the C-Br bond to have partial double bond character. You see, this explanation is the exact same shit that we write in. Okay, guys, so what you have partial double bond character? Let's break this apart. Tear it apart. So what partial double bond character means? Okay, it is very strong. Okay, which strengthens the bond, making it what? Good. That's what we're trying to get towards. We're trying to tell, I'm trying to explain why the bond cannot break. Why is it unreactive? Why cannot break? Okay. This is the full thing. Okay, then you can get full credit. Okay, but I'm aware that this question they ask for two reasons. Again, this is the more important reason. The second reason, much easier to explain. Okay. Okay, we talk about the second reason also. It is also in your notes. Guys, this reason is also known as the what factor. This whole thing. Yeah, this is the first out of two reasons. Okay, this is also known as which factor? Okay, the electronic factor, good. Okay, the other one is called the what factor? Something like that. Okay, it's not steric factor, it's your words also.
Yeah, I think
Guys, the steric factor, I've already written something similar in your notes. Okay, I mean, we have written it in class. I want you guys to write the answer for the steric factor. Then we can just move on. Okay, it's right there. Okay, so now you all can really feel the pinch. You can do the notes without, and if you don't do the tutorial, everything is useless. It must do both one. Okay, after this, we're going to try one more question. Or maybe two more.
Oh.
Okay, there's the steric factor as to why, right? Okay, this guy cannot undergo neutral sub as well. Okay, but before we get into that, I think there's something I also want to talk about. Okay, guys, you all know, you all understand this diagram already? Okay, it's directly attached, so the p orbitals can overlap continuously. This one, why is it that this guy doesn't have the same problem? Basically, this guy is like blocking the continuous overlap, right? Okay, you have these two guys having overlapping p orbitals. Okay, that's how the pi bond comes about. This guy also has his p orbital with low pair, but why can't this guy delocalize inside? Good. Okay, the middle one, why does he have a p orbital? Because this middle carbon is sp3 hybridized. Does he have a p orbital? No. Okay, no p orbital, no delocalization. Okay, so think of that right in your other structure as well. Okay, but let's take a look at steric. Okay, and we're gonna write it inside later. Okay, steric factor is what? Okay, there will be repulsion. Guys, why is there repulsion? Okay, so guys, a nucleophile, nucleophilic subnucleophiles are rich or poor? Okay, rich. Let's just say I have a OH minus nucleophile, and let's just say I have this exact same diagram. What happens? If this guy tries to approach, what will happen? Repel away by the what? Okay, good. The pi electron cloud is also rich, right? If this is rich and this is rich, there's going to be repulsions, and then the approach cannot happen. That's the answer. Okay, so you can see incoming nucleophiles will be repelled away by the pi electron cloud. Okay, but the thing is, this one has to approach this carbon over here. But this one over here is this carbon. It can basically avoid this. That's why I say, yes, you can even tell me, yes, you will still be repelled, there's still the influence. And that's why I say the steric factor is not the most. The more important factor is this. You can see how this is way more convincing. Yeah. Okay. Again, by ask for two reasons. Because that's why I say that's not the best. Yeah, because you are not wrong. You guys are not wrong. Yes, it will still be repelled, right? I can totally agree with that. Okay, that's why I say the second one is more. The first factor that we did is a lot more convincing. This bond is a lot easier to break. Okay. Okay, that's it. Just one statement. Okay, once you're done with that, I want you guys to now take a look at question 6. We will be looking at distinguishing tests. Then we've also done a segment in the notes that's about distinguishing tests.
I don't see.
It might even be your school before those. Okay, so let's take a look at part A. The part B. Part B is very common. Okay, come do part A first. That means y'all do it now. Your school tutorial must get it correct. Okay, draw the skeletal formula of the compounds as well. I want you guys to make it a habit of where if you see a structure, just change it to skeletal. Yeah, it will pay off in the long run. So now it's just a practice section. Okay, remember for distinguishing test, this is how you express your answer. Okay, first you must tell me what's the reagent and condition you decide to use. Afterwards, you give me your observations for both structures. Okay, the first structure is this. Second structure is this. Each structure must have an observation. Okay.
But then so you're gonna explain like why you
Yeah, okay, you don't have to tell me the rationale for each step one. No, you just need to give me the recipe. That's it. Okay, recipe, and then what you actually see at the end of the reaction. Hey guys, what's the answer here? What we use? Okay, so all three things must be mentioned. You're trying to distinguish the halogen alkane, right? Okay. I want you guys to write down more answers because clearly this is not the only answer. You can either choose to distinguish the halogen alkane or choose to distinguish the alkene. Alkene we have learned before already, so let's just use this as recap. Okay, many answers. Okay, but if you want to choose halogen alkane, this is the only method. Okay, we add dilute HNO3 for second stage, third stage HGNO3. That's it. What's the observation that you use? What? Okay, so YPPD off, you must tell me what exactly is that. Yeah, ATCL observe. Okay, then you're like, just tell me what, no YPPD. Don't tell me no change, don't tell me no observable change, don't tell me nothing happens. You just need to write the opposite of what you wrote. Okay, but then don't need to write ATCL here. Okay, but obviously there are other answers. Okay, so what are the other answers? Let's go over to the LT side.
Is it modern state?
If you want to lah, it doesn't matter. Yeah. Now think of alkenes, okay, if you think of electrophilic addition, is there a reagent you can add, right, that will somehow have a color change or some sort of observation? Yeah. Okay, BR2. Okay. Okay, so let's choose BR2. Okay, if you choose BR2 liquid, right, that one will be reddish brown. All your data nucleus. If you choose BR2 aqueous, this will be orange. Just orange. Okay, orange is if you dissolve bromine in hexane. Okay, all this again in your data booklet. Okay, come. Again, it's very obvious. This one there's no reaction. This one brown, orange, or reddish brown. The one very obvious. Okay, but there's other reactions, right, for distinguishing the alkene. This reaction right here is for electrophilic addition. Is there something else that you can do as well? What else can we do? Are there other reactions that alkenes can undergo? We have in fact gone through one just now also. Let's talk about the other one. What else? Alkene. Yes. What else did alkenes undergo just now? In the previous question. Addition is this one. Elimination, no. Elimination is for halogen alkane. Now we're talking about alkenes. There's another one. Come. No, it's Yuven's favorite one. Okay, so oxidative cleavage. Okay, guys, that one also got color change. Why? What's the color change here? Okay, so you put your KMnO4 H2S4 and B. There's no. Okay, in this case, good, that is carbon dioxide. Okay, come. For this oxidative cleavage, let's take a look at the observations for this particular compound. First of all, what will always happen when the oxidation is successful? The purple
I say like purple chemical.
Okay, you just tell me purple KMnO4 will decolorize. Okay. Purple KMnO4 decolorizes, but there's also an additional observation for this question. What is it? Just now someone mentioned why. Okay, someone mentioned carbon dioxide. Why? Why is that carbon dioxide here? Good. Okay, you notice for this particular alkene is terminal. Now, guys, for other alkenes, you might not have a terminal alkene, so just be very careful depending on the question. Okay, so here, other than purple KMnO4 decolorized, there's an effervescence of CO2 gas. Okay, we'll write this down also. As for the halogen alkane, you don't see shit. Okay. Okay, all good. Can I go and try part B now? Okay, express your answer the same way as before. Good. Yeah, go ahead.
Later, I want my.
Nice try. Good. Oh, yeah, yes. I said it was. No, it was the same thing when you said. Then write the answer. Make sure observations are correct. Okay. Other than how do you know the color change within different colors? It's not very noticeable in real life. Cream and yellow. Yeah. Yeah, I know cream is a very difficult color to tell. Usually, if you do both experiments, you can tell based on the color change. But there's a more conclusive way of doing it, which is to dissolve all these precipitates in ammonia. These precipitates have different solubility, so they dissolve in different concentrations of ammonia. That's the more conclusive way. That one we actually learn also. Yeah, like for example, your AgBr is cream, right? Your AgI is yellow. Now, AgBr, right, can dissolve in concentrated ammonia. However, AgI is insoluble in concentrated ammonia. So that means you don't know what's cream, what's yellow, right? Never mind. You add concentrated ammonia, you see which one actually dissolves. Then you know that one is cream. Does that make sense? This is the more conclusive way. Because yes, there is an issue of not being able to tell. Similarly, if you can't tell between cream and white, what will you do instead? AgCl we know can dissolve in dilute ammonia. So what will you do? Yeah, you just use dilute ammonia, and then the one that dissolves is AgI lah. The one that doesn't dissolve, your cream precipitate, is AgBr. So that's the way you can tell. Okay, but you don't have to notice this over here. Okay, but yes, okay, can you all just tell me what's the answer for this one? Okay, again, it's the same 3 steps as above. Okay, that's the reagents and conditions. Okay, but over here, what's the observations for
First one is yellow.
Okay, good. The first one is the yellow PPT of AgI. How about the second one? Okay, good. Okay, guys, there are so many halogens here. Why do you all purposely choose these two? Okay, good. Okay, this question is meant to trick you guys up. You are supposed to be looking at the halogenal alkane and not a halogenal amine. Because what happened to this halogenal amine? Can this PR come out as an ion? No, if it doesn't come out as an ion, there's no way you can form the precipitate. So it's the same thing over here. The only one that can come out as a precipitate is the halogenal alkane. So you only focus on the circled portions and ignore the halogens that are directly attached. What's the concept behind this? Why are they stuck there? Partial double bond character. Exactly. Okay, this is what you're asking yourself every time you do this question. Okay, reagents and conditions, same as work. Right, okay, so that's the answer for this question. Okay, so far. Right, okay, I want you guys to try one more question, right? Okay, before we actually take a break. Right? Okay, all doing okay. Right, I want you guys to now take a look at level up question 1. Okay, from here to the end of the lesson, we're going to start on other questions already. We try one MCQ that isn't as simple as it looks, and then later we can proceed. We can go for a break. Okay? Those who are there already, try this level up question 1 now. I want you guys to read through the question, see what the relevant concept is. If you all can spot the relevant concept, it's good enough. Right? Okay, you'll notice whatever you study the notes, right, sometimes can be quite pointless. The moment you see an exam question that stumps your ass, okay, the moment something shocks you, right, okay, you can't do already. So quite dangerous. Okay, that's the reason why you guys can't do tutorial questions. Okay, question 1 of level up, yes. Okay, I want you guys to read through the question and later I just ask you one question. What is the relevant concept here? Halide is just the X minus, the Cl minus, Pl minus, I minus. That's what halide is. Okay, so you read through the question already. This is not an easy question to look at. Let's break it down first. Now, they take a compound. Now, the compound can be any one of these 4 options, and they first heat it with NaOH. Guys, what's the purpose of heating it with NaOH? Any of these halogen containing compounds, heat NaOH, then what happens? Okay, you take a random halogenal alkane like this guy, you heat with NaOH and heat. What's the purpose of doing it in this question? What do they actually want? Okay, to break the Cl bond, right? Okay, so that you can get a Cl minus S ion. Then what did they do afterwards? After this first question, first statement. Okay, they add the silver nitrate, which is to form the. Okay, good. You add AgNO3 in order to form the AgCl, which is the white color precipitate. That is what they are tracking in this graph. Can see that one? Okay, then the thing is, they straight away gave you guys a graph. That precipitate, right, using two different concentrations of NaOH, they have two different graphs. What does this graph, right, actually tell you? Because the moment they give you this graph, the next thing they say is find the exact graph. There's so many missing links over here. Our job now is to first, right, understand what this graph is trying to get at. Guys, what is the difference between these two graphs? Okay, good. The rate at which the AgX precipitate forms is different for a different concentration of NaOH. Okay, so that's the number one thing. We are looking at rate. Who is faster? Okay, the solid line is faster because it has a what? How do you know it's faster? In other words, the gradient is steeper. Okay, guys, please take note of this is how you interpret graphs. Okay, a steeper gradient here implies that the solid one is faster. How about this one? Okay, the dotted line is definitely slower because it has a gentler gradient. Okay, so clearly, guys, what caused the difference in rate? Who is the main cause? Who's the main perpetrator over here? You change the concentration of NaOH and somehow the rate was changed. It so happens that when you double the concentration, the rate also increases, right? So this is what's happening here. Let's just write down this statement first. When you increase the concentration of NaOH, the rate also increases. Now, guys, just based on this statement, what can you tell? So that's when the question that I asked earlier comes into play. What is the relevant concept in this question? Okay, there's something about kinetics. Where was kinetics even talked about in this entire topic? Good, SM1, SM2. So that's the relevant concept here. We are going to try to look at SM1, SM2. Based on this statement here, can we deduce whether this reaction is SM1 or SM2? Is what? How do you know it's SM1? No, it's not. It's not. It's SM2. Okay, how do you know that?
What SM2 the rate was?
Not as an equal to nucleophile, but the fact is the nucleophile's concentration affects the rate of an SN2 reaction. So guys, take a look up. SN2 nucleosub is this reaction that's happening here. Why? Because the concentration of the nucleophile affects the rate. Can you see that? So guys, what on earth is happening here? Okay, if it was SN1, I want you guys to think of the other side. So let's not move on from here yet. If it was SN1, can someone just tell me how this graph would look like? Good, exactly. No matter how much you change the concentration of NaOH, SN1 don't have the nucleophile in the slow step. So it will not change the rate. Okay, now our job is still to find the exact structure. Now that we know that this is an SN2 nucleosub, is that a property of SN2 that we have learned in the previous lesson? Good. To determine what kind of halogenal alkane it is, we know that SN2 nucleosub is generally favored by primary halogenal alkanes. So let's find that primary halogenal alkane, and then that's probably our answer. Okay, guys, let's take a look. Is this a primary halogenal alkane? The first option. Is it? What is a halogenal alkane here? Primary, secondary, or tertiary? Secondary, good. Okay, so perhaps not the answer. Okay, let's take a look at B. Right? Okay, because this guy has two alkyl groups bonded to B. Okay, how about this one? B is tertiary. Clearly, probably not the answer because tertiary tends to favor what? SM1 reactions. Probably not the answer. Okay, how about this one? Okay, this is primary over here, so C the answer. No, it's not. Why? Look at the structure carefully. What's happening here? Look at the halogen. It's bonded directly to the double bond. What does that mean? Can this bond even undergo nucleosub in the very first step? No. Okay, so when they go over here, this structure has partial double bond character. What would the graph in this question look like if you use structure C? There'll be nothing. There'll be no precipitate in the first place because this guy cannot undergo nuclear sum. So don't just look at the primary one immediately. You must look at it carefully. So it's the answer option D. It is still not option D also. Okay. So what the answer is the friends you make along the way. Help lah. Yes, it's not option D also. Guys, why? Look at it carefully. Is this a halogen alkane now, guys? Look at it. No, that's not a halogen alkane. It's some sort of salt. Okay, what I'm concerned with is the Cl minus. Now, notice this is Cl minus. The rest of them the Cl is bonded to the structure. But this is the only time where the Cl has already liberated. So guys, how does the graph look like if you were to look at structure D? It will start hard. Exactly. It's okay, see you all know why it takes time for it to form the precipitate. What is this time taken for? Exactly. It's for the Cl to break. You all remember Cl bond quite strong. Okay, it takes some time to break. So the time taken over here is the way I write this also. Okay, the time taken is how? Okay, the time taken is for the CCl bond to break. So if you were to use this one already liberated, there is no need to break it, so you can skip all the weighting, and that's why the graph will probably look something like. You're going to draw the graph. The moment you add AgNO3, the graph will start from where? Like already the maximum. It's instant. You hit the maximum rate. What is the best answer? Answer C. Because we already mentioned guys, secondary halogen alkanes, which one do they undergo? SM1 or SM2? It's a mixture. Either one is possible. So guys, that's the best answer. Guys, this is not an easy question. I know. It's not. It's a grading question. Okay, it's a difficult question. Okay, yeah, from ACJC, I never knew this fucked up at schools. Okay, but yeah, true. Okay, don't read alright, some of these kind of question. Yeah, okay, I know this one is not worth it. Yes. Okay, but still need to go through that. Yes. Yeah, okay, it's not worth it in the exam, I know. Okay, but I can understand all this. It's not, the question itself is very well set, I think. Okay, all good. We take a break first. Okay, so let's take like take a break until like 5 minutes. Okay, 5-minute break only. Okay, we can do a slightly easier question first, which is question 2. And compared to question 1, 2 is a lot easier now. So this I think you all can do yourself. Come, pass game. Settle, finish, ready, we can end for today. Okay, we're gonna do question 2. MCQ also very simple. Oh, last year a lot more. Yeah. Can go many other questions to do. Okay, come take a look at question 2 MCQ again. Not very tough. Not very. Yep. That's all. Probably about 2-3 minutes.
video. That video. Fuck you. If you want to move, why not?
No, in A.
All three.
Yeah. But not.
What is my video?
It's not. 1 minute, think of the answer again. Don't anyhow whack. Look carefully at the options. Okay. Okay. This is B, bro. Okay, come, let's go through the answer. Option 1 correct?
Yes.
Okay, so X and T we already know. Why can't they form precipitates? Okay, partial double bond character, all that. Yes. Okay, so option 1 correct. Option 2 correct or not?
Yes.
No, it's not correct. Guys, what's the white precipitate? Okay, a white precipitate is AgCl. AgCl the fastest precipitate they can form here. So only W and Y can form precipitate. This is AgI. So AgI is faster. Why is that so? Oh. Rate of reaction. Why is I faster? Yeah. Okay. This one need to break a CCl bond. This one need to break a Ci bond. Ci bond is weaker than the CCl bond, so clearly it is faster.
Yeah.
Can see that? So 2 is wrong, The color of the precipitate which forms the fastest is what? Yellow. Okay, good. You must remember the colors really. So third one, precipitate which forms the fastest. What is that? What's the one that forms? Okay, AgI. Go and like write it down. AgI. So you don't need to read the question again. Okay, AgI weighs more than the other. What's the other precipitate? Does AgI weigh more? Does I is bigger than Cl. So C is correct. 3 is correct. Go look at your periodic table. Okay, I is below, very, very heavy. Okay, can? Okay, so it's not very simple. Right, compared to just now. Okay, so clearly. Okay, can so far?
You're just guessing around.
No, you have one. No lah. Okay, come. I want you guys to take a look at question 4. Actually, no lah. Let's skip that first. Later, maybe we can try. Okay, go to question 7. We go to the bottom one. I want to do question 7 and I think 12. Okay, then we will be done for today. See how long it'll take. Okay, let's look at question 7 first. This one quite okay. Yes. Okay, correct. Question 7. I want you all to take a look at A part 1. Just A part 1. Oh, no, wait. Actually, first. Question 7. I want you all to try to draw 1 chloroethyl benzene. Because this one, a lot of people make mistakes. Okay, that's our first task. Just draw that compound. Okay, come try. Okay, the bracket or no bracket doesn't really matter. I'm just gonna write without the bracket. Okay. So ethyl how many carbon? That's what you are asking, not the line. 2 carbon. Okay, when you break down a name, you must always read from right to left. I already mentioned that before. Okay, the right hand side of the name is the most important. The left hand side of the name it should be filled up last. No. Close. And that's the one that most people draw. That's what I draw.
I think it's not right at the start.
No. You can't have the carbon on the benzene now has 5 bonds. But no, cannot.
Wait.
Yeah, a little bit tricky, this one. Wait. No. Not also. Yeah. Can you do this?
Is it?
Guys. Yeah, that's the one.
Oh, let's go.
I mean, that's the only other option left, right?
Yeah,
Why? Why is it? Okay, this is what people will do. Okay, guys. First of all, I need you all to draw. Look at the right hand side of the name. ethyl benzene. What is ethyl benzene? A benzene with how many carbons is ethyl? 2. So let's just attach it anywhere. 2 carbons attached to the benzene, that's ethyl benzene. Very simple. But now the difficult part is how do we fit 1 chloro on the ethyl benzene? 1 means on the first carbon, but where is the first carbon? Some of y'all, okay, I've seen one that says here, no, it's not do anything. The 1 carbon is referring to which carbon? It's on the ethyl group. There are only 2 carbons here. It's either carbon 1 or 2. Is this carbon 1 or is this carbon 1? A lot of us will see that this is carbon 1, so you put your chlorine over here. Okay, which is I want to make you guys first okay, N lah. That's why you call that number 1. However, it's not always the end of a compound, right? Where you can call it number 1. It's just not. You must do this as number 1. Why? Because before I put the Cl inside, this carbon here is bonded to the benzene. This carbon is not bonded to anything. So carbon number 1 has more priority. Can you see that? Does that make sense? Carbon 1, as long as it's bonded to something else, that means this carbon has more priority than the other one already. So this right here is 1 chloro dominant. Now that you know how to draw this compound, I need you guys to look at part 1. You need to outline the mechanism involved. Okay, you don't need to explain whatever yet. I just want you all to outline the mechanism. Meaning to say all the arrow drawings that we did 2 days ago. Okay, yes, you need to draw the full mechanism. Okay, we have learned how to draw mechanism already for nucleoside. Okay, give that a try. Yeah, by the way, next week always is 2 for you okay, right? I think I'll ask them to do. Most of them okay, okay, because someone else need to see the lesson also. Yeah. So yeah. Well, it's just my other students. There's one other girl who wants to see it because I need to combine classes really. Start to combine classes. I mean EJC, but we're all doing the same topics. So. Yeah, so eventually the class is going to fill up with more random people. Not that many more. Yeah. So if your friends do want to start immediately, get them to fill up the class really, then won't have like a lot of random people joining the class. We outline the mechanism involved. Okay, about 3 minutes to try this. Okay, you must first write the title of the mechanism. Okay, there are 2 mechanisms for you all to choose from. Obviously, it's either SN1 or SN2. Okay, but which one you must go and check. Hey guys, let's discuss first. Is this SN1 or SN2? You must decide. Whether it's 1 or 2, okay, what's more important is you must find clues in the question to help you guide you towards the correct mechanism. If you say SN1, why you say SN2? Okay, but again, let's argue the other way out. Is this primary, secondary, or tertiary? Okay, so most people will look at this first. To decide between SN1 or SN2, most students will say whether it's primary, secondary, or tertiary. This right here is what? Okay, secondary meaning, is it conclusive? No, it can be either, so we have to look for other clues. And the clue that Harshit picked out is correct. Okay, so the question says here race-mate mixture. Which one has race-mate mixture? SN1 only. SN2 don't have such thing. So that means the answer here to this question is SN1 nucleophilic sub. Now guys, we have already explained in our previous lesson how this race-mate mixture is formed. So this question is made up of 2 parts. That's why it's 4 marks. Later on, I need you all to try to explain how the race-mate mixture is formed. We went through that before, but first we need to see the mechanism come up. Okay, give it a try. Yes, it is a reagent condition. This one is to form nitriles. Right? No. Okay, remember both reactions, SN1 and SN2, were 2 reactants. How can you have just 1 reactant? You're not going to react shit. It's not about 2 reactants, remember. It's 2 reactants in the slow step. Then it's SN2. One reactant in the slow step is SN1, but SN1 still has two reactants in total. Okay, so don't just count the number of reactants. How come your notes like of course they are like this, but you go and transfer everything to the notes. Okay, let's try to draw a bit bigger, like I said, because sometimes the arrow cannot be seen properly. But okay, answer is correct. But again, this arrow, I feel that you're pointing. I don't know whether you're pointing to the plus or the carbon. Yeah.
So basically, that's not
It must be very clear to point to the C. Yeah. Okay, let's take a look at how this works. Remember, SN1 has how many steps? 2 steps, huh? A 2-step SN1 nucleosub. First step, okay, remember, what does the one in SN1 hey guys, what does the one in SN1 mean? One what? One reactant in what, the whole reaction? In the slow step only. So in this case, you should only draw this species. Okay, so let's just draw this out. Okay, so clearly, you only involve this one reactant, and this one will be your slow step already. In SN1, you form the carbocation intermediate. So how it looks like is this. Okay, remember that this carbon is partial positive, this one is partial negative. The electrons in this bond will just break and then just go towards chlorine by itself. It doesn't have any other like provocation from a nucleophile. So when this happens, what happens to this carbon atom? What charge does it have? Okay, what charge will the carbon atom gain? A plus charge because it has now lost an electron. So it looks something like this. How about the Cl minus? Oops, it's here. Okay. Okay, but after this, after you form the carbocation, in the second step, what do you guys need to do? Is there something that affects this carbon with a positive charge? Okay, what's the nucleophile? Okay, good. In this question, what's the nucleophile? Yes. Cn minus. Okay, so take Cn minus, where's the lone pair? On N or on C? Okay, it's the lone pair on N or C. Okay, it must be on C, lone pair not on N because it's not bonded to N. So take the lone pair and I want this guys, right, attack the carbon up. So you see how my arrow is drawn? My arrow purposely move towards the carbon. I purposely bring through the positive charge. So make sure it is clear. The moment, right, I don't see the arrow very accurate, like one of your answers are immediately give it wrong. Because it's what I chose to do in example. So, okay, so this will be your first step. And then it is a simple substitution done. Okay, now guys, this right here is 2 marks. The next 2 marks is to explain how the racing nature is 4 marks. Okay, I'm only going to go over the keywords because the answer is already. Okay, come quickly write down a sample answer. How a racing mixture is formed. Okay. Okay, all the keywords that I mentioned in the previous lesson must be your answers. Okay, so come, let me see all your keywords. Yeah, so. Okay, first game, we still have another big question to try. All the keywords. Okay, that's one keyword. Okay, come on, write a cohesive answer. Yeah, all this mechanism stuff come on Monday. Yeah, go and watch the lecture when you go back. Yeah, then the tutorial question might want to try again. Because now maybe a bit blur. Uploaded already, I think. Yeah.
What's the FAO for?
Geometry.
Yeah,
You want to say the shape of the carbon cation, just say shape. You say the geometry, no need, no need so fancy. You won't get extra marks for that. Yeah. Again, I already highlighted the keywords that you get marks. Guys, you all should remember how the recipe picture roughly looks like. I'll show you guys the pictorial representation also. The nucleophile can attack from the top and bottom with equal probability. But why? Why can it attack with equal chance? Because it's planar, it's flat. Okay, so all you need to tell me first, this carbocation is the one that's getting attacked from the top and the bottom, right? So it all starts out because the carbocation is trigonoplanar. That's the first keyword that I heavily emphasize. And because it's trigonoplanar, okay, then you can tell me about the rest. It does the nucleophile. Here is minus, so you can put in a little bit more specifics here. It can attack from either sides of the plane with equal probability. And because of that, it results in what? Okay, that's where the last keyword comes in. Racing mixture is formed. They are both enantiomers, like you form two enantiomers, but these two enantiomers are equal proportions. Yeah, okay, but you don't have to note it, you don't have to write that. Because this explanation like that is sufficient already. You cannot planar attack with equal probability racing mixture. I did tell you guys that these are words. Okay. Now we're gonna talk about part 2 together. Okay, this one quite important also. Okay, this one we also discussed last lesson. Okay, for part 2. Okay, so finish this up first. It is A part 1. Now we're gonna look at A part 2. Okay, guys, let's look at the question first. Explain why it proceeds via this mechanism. What is this mechanism they're referring? Okay, good. So let's rephrase the question. They are asking, why does this carbon or why does this product of compound favor SN1 mechanism? Now, we already mentioned this is a secondary halogenal alkane. It can proceed via the option, but here you're supposed to justify why SN1. Guys, can you remember what this falls under? Remember the quadrant, the table? Okay, yeah, that is we are trying to argue why it prefers SN1 over SN2. Now, there is no concrete answer for secondary halogenal alkane, right? But remember, when you want to answer this question, what's the factor you're supposed to talk about? Here the question says SN1. So SN1 you must discuss. What's the factor? Now SN2 was the factor, can you remember also? Okay, good. SN2 was about steric hindrance. You argue whether there's high steric hindrance or low steric hindrance. SN1 is about what? Something to do with this guy. Good. How stable the carbocation is. So factor you have to discuss here, stability of the carbocation intermediate. Can see that? Okay. Now guys, if this guy happens to favor SN1, it means the carbocation is very stable. can see what's going on first. We're supposed to argue why it's stable. That's why we ended up favoring SN1. So stare at the carbon pair ion that you've drawn just now. Why is this guy stable? Sorry? Okay. Now, remember, guys, we know that this guy is stable, so let's work backwards. Okay, he favors SN1, which implies the carbon pair ion is stable. Okay, come, let's just build our answering here. Okay, again, this one is just the thought process. Later the answer we can write down one more time. Okay, it favors SN1 because it's stable. Guys, why is it stable? The positive charge must have been not donated. What's the word? Also starts with D. No, not delocalized. This curve. Okay, this first means the charge is big or small. Small. Okay. Now, write this down. If the carbon pair ion is stable, it implies that the positive charge must have been dispersed to a large extent. Guys, what could have possibly caused this? Okay, this question here, something slightly new. Okay, I'm going to tell you guys about this. So this A part 2 are extremely important. Okay. How is the positive charge dispersed to a large extent? Guys, positive charge is rich or poor? Okay, good. It's poor. Now, guys, this carbon here is poor. In order to disperse it, that means something must give electrons or take electrons from it. Give him electrons. Agree first. Okay, you give him electrons, you satisfy him, then you become more stable. But the issue is, guys, okay, from now on, when you all see a plus charge, right, that's directly attached to benzene, or in fact, anything directly attached to benzene, a high chance it's going to be localization. Okay, so let me just show you guys how this works, because this part here you haven't seen before yet. How you disperse this positive charge is because there's going to be p orbital overlaps, and what happens? The lone pair delocalizes. Now, guys, just take note of delocalization, just like any other electron movement in chemistry, must always be from rich to poor. So can you tell me the electrons delocalize from where to where? Is it from the carbon pair ion to the benzene, or from benzene to the carbon pair ion? Good. Benzene is rich, carbon pair ion is poor. So I need you guys to maintain this in your mind. I'll give consistency here. Okay, how you give this guy electrons to make him happy? It's because benzene give him the electrons. So you must tell me this first. The p orbital of the carbon pair ion overlaps with the what? Overlaps with what? High electron part of benzene. So what? So pi electrons, okay, before that, from where to where? Okay, good. Okay, pi electrons are delocalized from benzene to the carbon pair ion. That is how the positive charge gets dispersed. And that's how you stabilize the carbon pair ion, and that's how it ends up favoring SN1. So guys, this part over here is a little bit new. Now know anything attached to benzene probably need to discuss delocalization. You might want to draw this diagram inside also, where there's p orbital overlaps. And the electron movement okay, is from benzene to the carbon with large charge. Okay, tricky question again, put a star next to it. That's why this is under level part. You can see the flow first. Okay, your answer should be written backwards up. Okay. Okay, might not have time for part B, but part B is kind of similar anyway. Okay, I wanted to go through part A and the whole of part A. Okay, write this down first. Anyone who's done already, I need you all to turn over to page 12. Okay, sorry, question 12. I always say page 12. Yeah, okay, question 12. As you can see, there are many exam style questions. Okay, all these are slightly harder. Your job is to really ensure that your level 1 questions you all can do properly. Yes. Okay. Okay, some of it you can see is prelim questions. Prelim questions are tough. Okay, I don't really expect you guys to be able to do prelim questions now, right? But eventually we will have to. Okay, so minimally, guys, your goal for this topic, right, is to really go and study all the reactions, consolidate them, and make sure level 1 questions you all can do. Okay, with level 1 you all can do yourself. Level 1 questions. Level up, eventually. Okay, level up is tougher. So I'll do it again.
Oh, I didn't see that one.
Yeah, okay.
Wow.
So guys, come take a look at question 12 now. Okay, a little bit, we have 10 minutes left. I'm gonna pick out certain parts over here. Okay, we're gonna skip like part A, definition question. Okay, that will be pointless. Okay, wow, you go foul, no already. Okay, okay, nice try. Okay, what you want to do? 12B part 1. Okay, because later I want you all to do, okay, just B part 1 first. Because on top of B part 1, right, we'll do part C and part D. Okay,
B part.
yeah, B part 1 only. No, very, very fast. Okay. Okay, reaction synthesis similar to what we did earlier.
Oh, I say.
Just call it Q.
Yeah,
Q. That's true, brother right there. Brother right there. Kind of gay, kind of like central, yeah. Do anything for boys. The time meeting was like really complimenting your ass. You said it and you were saying like, wow, why is that thick?
Wait, who?
Oh my god, guys, stop looking at each other's ass.
Yeah, that honest.
Nigga, what's the I can tell people. What? It how deep part 1. This one is actually just a one-step reaction if you want to. Yeah. Okay, because that's not really the point. The point is part C and part D. Okay, so okay, they told you what the starting compound is, right? Okay, which is bromoethane, which kind of just looks like this. And then they want you to turn it into this. Alright? Okay guys, how do you turn bromine into a ADP? Okay, what nucleophile do you use? Obviously. Okay, not nitrile, nitrile is CN. Nitrile is CN. NO3. Nope. Guys, you just need to add what? Ammonium, right? Guys, one of the reactions. It's one of the nucleophiles that we learned, one of the 3 nucleophiles. So over here, okay, this one just go and copy and paste your radius and conductance. Ethanolic concentrated ammonia. And you heat in the what? For ammonia. Seal tube, yes. Need to prevent ammonia from escaping. Now this one, right, is just a reaction here, but more importantly, I'm more concerned with part C, okay? Because part C is the follow-up to this. Okay, go and try part C now. Describe the mechanism, more arrow drawings. Describe means the drawing of arrows, SN1 and SN2 you can draw. Like what we did just now for SN1 for question 7. Yeah. Very quickly, I'm gonna try to draw. It's the part D.
They don't draw the you get one. Not what?
That one is for which one? SM1?
In the base.
Right.
I don't know.
Okay, guys, it's SM1 or SM2? Okay, why SM2? Okay, they never give us any information in the question, so you just assume based on the generic properties. Okay, over here, primary halogen alkane must be SN2 nucleosub. Okay, spell the whole thing. Okay, guys, remember for this one, right? I did mention that this is not an easy mechanism to draw. Not like SM1. SM1 is a lot easier. So here, do remember the way you position the bonds. It just looks like this. Okay, so I suggest, right, okay, position the bonds like that first, and then you fill in all the other groups. You do need a bit of space on the left hand side, because remember your rear side attack. Okay, so the one on the right hand side here, just put your halogen alkane. Then the rest, right, okay, you can do something like this. Put your alkyl group and your two H's. In other words, I am using this carbon here as the middle carbon. Why is he the middle carbon? Because that guy is going to get attacked anyway by the nucleophile. Okay, and you must draw this stereochemical formula because I did mention that this is part and parcel of SN2. Now, what is the nucleophile involved over here? NH3. Remember, rear side attack, because that's the property of SN2. You attack the poor carbon, but you must show me why the carbon is poor by showing me that partial charge. Once you have attacked this carbon, guys, what's the other arrow that needs to happen? Okay, CBr. Okay, this bond needs to break and the electrons go towards bromine. So that's the first stage arrows. Right? Give me your slow step. And then what's the next thing they need to draw? Okay, your transition state. Okay, transition state, I'll remember, is the period of time where you haven't really broken the bond yet, and you also haven't really formed the bond yet. So that's why the bonds must draw using the dotted lines. Dot, 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 dot. Can see that? Yeah. And the idea is this, okay? Remember, I did tell you guys also, the solid and dashed wedges have to be swapped because it's part of the inversion that is going to happen after this step. Okay? Solid and dash swap it around, but the groups still maintain the same. I'm just telling you all to swap the positions. Guys, is there an overall charge on this transition state? No. Okay, no, good, because overall it is neutral, so it should still maintain as neutral. Finally, let's look at the final step. Okay, guys, this is the step where the bond with NH3 is finally formed, and the bond with bromine is finally broken as Br-. Okay? Remember, guys, now everything just now is facing the left-hand side. Now everything must be flipped to the right-hand side. So now, position your bonds, everything now facing right. You can already see the solid and dash wedges have also swapped positions. Because that is your inversion of stereochemistry. But we're not there yet. We need to show the arrow movements for that. Okay, but let's pause it there for a moment. Can you all get until this point? Okay, can you get until here first, right? But guys, do you notice something as well? Okay, we did this exact same mechanism in class. What else happens in this mechanism? How come suddenly overall here got one negative charge? When over here it has been neutral, how come suddenly a negative charge is given birth? Okay, yeah, but how do you get there? Where does the H even come from? Okay, because what's happening here, there's something missing on this structure. There has to be a plus charge. Good. On where? N. Good. Okay, there has to be a plus charge on N simply because N cannot have 4 bonds, and we also justify it by saying this N has given away its own pair. The type of missing electrons means you must get a plus charge. Does that make sense? Okay, so we have to do our final adjustment. So this is the adjustment step that must happen. Okay, so NH3, let's draw all the 3 H's. Guys, can you all tell me what the arrow movement is once again? Okay, what's the arrow movement? Okay, perhaps okay. What's the final product first? This will make it easier. H2N, okay, good. And then the other product there? Okay, good, HBr. Okay, what's next then? You look at the final product here, then you can deduce how the arrows are moving. So how do the arrows move in this case? From the thing to H. What's the thing? Oh. Okay, guys, look at how does Br minus turn into HBr? I mean, no. Not that. Okay, so first, how does Br minus turn into HBr? It has to get together with a H, right? Whose H? Where? Which H? This one? This one? Anyone from any street, because eventually one of these guys can be stolen away to become 2 H's. So I should see or no pair attacking this H over here, for example. Can? But something else must happen. What else must happen? The moment this H is gone, this bond is useless. What can we put these electrons for? What can we use it for? How can it be useful? Who needs these electrons? And you can put. That's the answer. Okay, that's your mechanism. Okay? Yeah. Yeah. Right? Guys, there's still part B. We are kind of running out of time, but let's just quickly look at part B. Okay? You can read through the question first. We can look at this together. Okay, then we can end off the lesson after this. Okay, part B is very important. Highlights the C8H20, the massive molecule. Highlight that first. Okay, and also highlight it gives an immediate precipitate, immediate DPP with AgNO3. Do you remember just now that long ass MCQ question that wasn't worth it? There was one scenario where the precipitate can form immediately when you add AgNO3. But we come back to that again. Okay, just maybe like recall that. Okay, look through the question one more time. The byproduct in the formation of this, okay, there's a byproduct that's 8 carbons big. What the hell? Okay, this only is 2 carbons. How come suddenly there is a way where it can turn it into 8 carbons as a byproduct? How the heck does this happen? Benzene, no. Why so nice 8 carbons? Okay, guys, let's break down the other thing first. Immediate precipitate with AgNO3. We mentioned this is one of the more interesting reactions in this topic. Guys, if you can form an immediate PPT with AgNO3, first of all, what on earth is the PPT? Okay, of course, it's AgX, AgBr to be specific in this question. Good. Okay, so how do you form this AgBr precipitate immediately? If you can form it immediately, it implies what? There's a Br minus, you can see that. Just now that question, we did the same thing. If you don't recall, just now this NaH2 plus Cl minus. This guy is the only one that wasn't bonded. So if you add AgNO3, it will form precipitate immediately. So from now on, I need you all to understand this. If there's an immediate PBT, it means there is a Br minus free ion. You can put the word free there to really get across the point that it's not bonded. It's not bonded. So that means, guys, this C8H20 and Br, this Br here is actually a what? Br minus. Can see that first? Okay, if this is Br minus, that means the rest of the molecule is plus. That's why the whole thing neutral. How come suddenly you can have 8 carbons from 2 carbons, and then the N got 1 plus 1? Can you remember this reaction? What is this reaction here? It's not just a step up. Okay, I know there's an increase in carbon, but not just we never learned a step up when you can go from 2 to 8 carbons. But there's this one reaction. Can you remember, guys? This guy still has a low pair. Does the reaction stop here? So what happened? It's the multi-substitution of this amine from primary amine, then you add another one. A wing. Remember the wing example that we used? From 2, it actually goes to what first? 4, 2, and how many wings is this? Then after that, then 6 wings, 3 wings will be 6 carbons because each wing we know in this case is 2 carbons. So 2, 4, 6, 8. And that's fine. That's the product we're going to draw over here. Primary, secondary. This is the quaternary salt.
We're supposed to draw the thing.
And we're supposed to draw the thing.
No,
Guys, always just don't need draw all the steps, okay? Just give me this quaternary salt. I'm going to give it a try. I told you guys how many wings it is really, right? So, okay, no, don't need all the equation. I just need that final product. So that's why, guys, I did foreshadow this at the start of the lesson, or the start of the first lesson. Okay, this is how to test this question. There are many clues here. The only one with a free ion is this quaternary salt. Primary, secondary, tertiary don't have this free ion. We'll put a star next to this question. It's very important. Probably 2. 2 marks is worth it, guys. 2 marks it's not easy to earn in
In the end, you answered that one.
In the end of the day, yes, your answer is just 1 marker. Correct. Guys, okay, in fact, they could be mean, they give you 1 mark for this only. That one not worth. Okay, but I will say it's 2 marks. Because they did ask you to write the equation also. Okay, screw the equation. Okay, you all know the equation, just refer to the notes. I just want the product. Okay, so guys, how does the product look like? How big is each ring? How many carbons is each ring, basically? We start off with 2 carbons, so 2 carbon ring, 2 carbon ring, 2 carbon ring, 2 carbon ring. And N has a what chart? Plus. But don't forget the other thing, which is we need the full structure. Br minuses 3 at the side. That's the answer. Finish.
Wait, but then the
It's not bonded, it's just a plus minus. Plus minus means just attracted by an ionic bond.
And then one is the right.
Yeah, that means the 4 equations to how it's formed. Can you remember?
You go right there.
No, not now. We screw that now. Okay, this one is more important. I need you all to see how to get here first. Okay, so guys, that's it for today. Okay, so next lesson we're going to start on the core J2 topic. It's called acid base. That one difficult. The acid base equilibrium.
Yeah, let's go.
That one tough, that one tough. The thing is, I usually need 4 lessons to cover one, but we only have 3 lessons in our curriculum. So it'll be quite